Good afternoon, everyone. My name is Zhang Qian from Shanghai Jiaotong University. I'm very honored to present our work, SoundLip, enabling word and sentence level lip interaction for smart devices. Nowadays, the voice user interface or VUI is becoming more and more indispensable to smart devices because it can provide an intuitive and convenient interactive way without any touching or typing. For example, we can use voice commands to control smart appliances, make a phone call, send a message. However, VUI is not ready for increasing demands since it still suffers several limitations. For example, it is not suitable to issue voice commands in some scenarios, such as in a library, or environmental noise will significantly degrade performance of speech recognition. What's more, voice-based interaction in public areas also has the risk of privacy leakage. To overcome these limitations, we present SoundLip, a non-invasive end-to-end lip input. The key aspects of our system are ultrasound sensing and lip input. As shown in the picture, when people are speaking, SoundLip leverages the speaker to transmit the ultrasound and simultaneously uses the microphone to receive signal reflected by moving lips. Then the system can analyze the reflex signals to recognize commands. Moreover, SoundLip can not only recognize the isolated word command, but also recognize the continuous sentence level command. Here is the system design of which consists of three modules: data collection, signal pre-processing, and lip command. In data collection, we use the EQ modulator to get phase and amplitude values. Moreover, we simultaneously transmit sound waves at multiple frequencies to mitigate frequency selective fading, as well as enhance the capability to profile multipath environments. When it comes to pre-processing model, we employ two simple but effective measures in this stage. First, we calculate the gradient of received signals to remove static multipath inferences. Then, inspired by time wrapping techniques, we apply data augmentation by wrapping the differential data along both the horizontal and vertical axis. A lip command recognition can be split into two different parts, word level and sentence level. In word level recognition, we design a hierarchical scene which contains two individual scenes and one limb merged scene. The two individual scenes are constructed to learn the intramodality information of phase and amplitude respectively, while the merged one is to find the cross-modality association between these models. In sentence level recognition, since it's hard to segment for each word, we treat the sentence level lip reading as a sequence modeling problem and adopt a multitask encoder-decoder network to directly map the acoustic signals into sentences in end-to-end way. The encoder and decoder are both based on RN with GRU unites, and we apply a multitask learning strategy which combines sentence and attention together. The next part is the implementation and evaluation. We develop a data collection app on commercial smartphone and invite 12 volunteers to construct two datasets which are word level and sentence level. The locations where volunteers perform the experiments contain four settings: laboratory, meeting room, bedroom, and living room. First, we evaluate the performance of SoundLip on the word level dataset. In the user-dependent test, we can see that SoundLip can achieve very high accuracy. In the user-independent test, SoundLip can still achieve about 19%, which means our system is robust enough to recognize the words from new users. Then we evaluate the word-level micro-benchmark on the user-independent test. We can see from the table that each component in our pipeline boosts the recognition performance to some extent. We also evaluate SoundLip in different situations. It can be seen that SoundLip is robust to different noises and also to different distances and angles. Secondly, we evaluate the performance of SoundLip on sentence level dataset. The test results show SoundLip is robust enough to recognize sentences from new users. Also, in unseen sentence test, we evaluated sentences not encoded in the training set. We can see that SoundLip can also deal with this problem. We also conduct the same comparison and robustness tests as those in word level evaluation. And last, we carry out system delay, impact, phone type, and wired performance evaluation. As a result, from these results, we can see that SoundLip works very well in real time. In a conclusion, we present SoundLip, a first-of-its-kind acoustic sensing system which enables end-to-end liberating at both word level and sentence level. We propose a single model and a multitask encoder-decoder to enable word level and sentence level liberating respectively. We construct two high-level datasets and achieve state-of-the-art performance under a broad range of evaluations. Thank you.